Hello, this is video number 25 on my single variable calculus 2. In this video, we're going to talk about Taylor series. Given a function f of x, we would like to create a power series for this function. We already have seen one example of such a power series. For example, if you look at the function 1 over 1 minus x, we have a power series for 1 over 1 minus x, and that is sum of x to the power of n. And that comes from the geometric sum. And that is true whenever x is between -1 and 1. So let's look at a couple of examples that uses this geometric sum to get power series for other functions. So we want to find a power series for each of the following functions. In each case, we want to find the radius and interval of convergence. If you look at the first one, we can think about that as 1 over 1 minus x squared. And now we're going to use this equality that we found here. So we have to replace x by negative x squared. So that would give us the sum n equals 0 to infinity negative x squared to the power of n. And the condition for x is if negative x squared is less than 1. So we can simplify this to the sum n equals 0 to infinity negative 1 to the power of n x to the power of 2n, and the condition becomes absolute value of x less than 1 if we take the square root of both sides. So this would be the formula for 1 over 1 plus x squared. The next one is x cubed over 4 plus 3x. We would like to turn this one into something very similar to the geometric sum. Geometric sum was 1 over 1 minus something. So in order to get 1 on top, we're going to factor x cubed. In order to get 1 at the bottom, we're going to factor 4. So we are left with 3/4 x. And all we got to do is to switch the sign from positive to negative and turn this into negative 3/4 x and then multiply it by x cubed over 4. Now this is a geometric sum, so we can write it down as sum of negative 3/4 x to the power of n equals 0 to infinity times x cubed over 4. And finally, the last thing we're going to do is we're going to write down this one in the form of a geometric sum, a power series, which is negative 3/4 to the power of n times 1/4, and then we have x to the power of n in the first one and x to the power of 3 in the second one. So we get x to the power of n plus 3. N goes from 0 to infinity. Now, when do we have this equality for geometric sum? When the common ratio is between -1 and 1. So this is if absolute value of negative 3/4 x is less than 1. Let's simplify that and see what we get. So we get 3/4 absolute value of x is less than 1. We are going to multiply by 4, divide by 3. We get this. So bottom line is x cubed over 4 plus 3x squared is equal to the sum n equals 0 to infinity negative 3/4 to the n times a quarter x to the power of n plus 3 if absolute value of x is less than 4/3. So this would be the final answer. And by the way, this was 3x, not 3x squared. Okay, so sometimes we can apply differentiation and integration to get power series for other functions. So let's look at these two examples. We want to find a power series for each of the following. If you look at the first one can be obtained by a power series for 1 over 1 plus x, and differentiating that gives us 1 over 1 plus x squared. So let's write down the power series for 1 over 1 plus x. This is 1 over 1 minus x, which is the sum of negative x to the power of n equals 0 to infinity. So this is the power series for 1 over 1 plus x. Now we are going to differentiate both sides. The left becomes minus 1 plus x to the power of -2. The right becomes n equals 0 to infinity. We'll have to differentiate this. This is negative x to the power of n minus 1 times -1 by the chain rule, and this becomes the sum n equals 0 to infinity n times, we have -1 to the power of n minus 1, and we also have another -1, so we can add the exponents, and this is x to the power of n minus 1. Now, simplifying that, we can write the left side as -1 over 1 plus x squared equals, and on the right we get n equals, for n equals 0, this expression is just 0, so we can ignore that term. So it would be n equals 1 to infinity, -1 to the power of n x to the power of n minus 1. And after we multiply by the negative sign here, we are going to get 1 over 1 plus x squared, all of that squared, is equal to the sum -1 to the n plus 1 n x to the power of n minus 1. So that is the power series for 1 over 1 plus x all squared. So the next thing we're going to do is to see what happens if we integrate 1 over 1 plus x. We know that when we integrate 1 over 1 plus x, we get natural log of 1 plus x. So let's do that. We start with 1 over 1 plus x, which we know is that 1 over 1 minus x, and then we can apply the geometric sum formula. And now we want to integrate this. So let me just write this down as -1 to the n x to the power of n equals 0 to infinity. Now we're going to integrate this one. When x is between -1 and 1, 1 plus x is positive. So when we integrate, we don't need an absolute value. So we get natural log of 1 plus x equals, on the right side, we get the sum n equals 0 to infinity, -1 to the n x to the power of n plus 1 over n plus 1. So that's the integral of x to the power of n, but we do need a plus on the right side. So now let's see what happens when we plug in x equals 0, because natural log of 1 is very easy to evaluate. So we'll plug in x equals 0 to see what we get on the two sides. On the left, we get natural log of 1. On the right, we get 0. Every term is 0 plus c. So that gives us that c is in fact 0. So we get a very interesting formula. We get natural log of 1 plus x is equal to the sum n equals 0 to infinity, -1 to the n x to the power of n plus 1 divided by n plus 1. So that is the formula for natural log of 1 plus x. So now in general, how do we find a Taylor series for a given function? So what we do is, let's assume that a power series is equal to a function. We can find these coefficients by repeatedly differentiating and substituting x equals 0. If you substitute x equals 0 into this function, into the right side, all of these terms become 0. So we get f of 0 equals a0. So that coefficient a0 can be obtained as f of 0. If you differentiate the function, you get a0 becomes 0, a1x becomes a1, a2x squared becomes 2a2x, a3x cubed becomes 3a3x squared. After you plug in x equals 0, all of these terms become 0, and we get f prime of 0 is equal to a1, so a1 is f prime of 0. So we differentiate again and substitute x equals 0. We get a2 equals f double prime of 0 equals over 2. We differentiate again, substitute x equals 0. We get f triple prime of 0 is 2 times 3 times a3, which means a3 is f triple prime of 0 over 3 factorial. Repeat, and we get a4 is f4 of 0 divided by 4 factorial. This gives us the general formula of an is fn of 0, the nth derivative of f at 0 divided by n factorial. The series fn of 0 over 0 n factorial times x to the power of n is called the Taylor series of f centered at 0. So that's the name of this series. Now, similarly, you can find the Taylor series of a function centered at a different point x naught, and that is by taking the derivative n times, evaluating at x naught, dividing by n factorial, and then multiplying by x minus x naught to the power of n. And the range is always n equals 0 to infinity. So let's do 3 examples on this one. These are very, very important examples for power series. So these are Taylor series for e to the power of x, sine of x, and cosine of x. And we want to find these centered at 0. So we'd have to use this formula, fn of 0 divided by n factorial times x to the power of n. So we'll start with f of x equals e to the power of x. Well, if that is the case, then its derivative is still e to the power of x. So that means fn is the same function. So now we are going to substitute 0. So fn of 0 is equal to 1. So the Taylor series is going to be the sum 1 over n factorial, fn of 0 divided by n factorial, times x to the power of n equals 0 to infinity. So this is the Taylor series for e to the power of x. It happens that in fact this is also equal to the function e to the power of x. So e to the power of x is the sum n equals 0 to infinity 1 over n factorial x to the power of n. Let's look at the next example. So the next example is sine of x. So this would be a little bit more complicated. If you take the function to be sine of x, we will repeatedly differentiate and then find a pattern. The first derivative is cosine of x. The second derivative is negative sine of x. The third derivative is negative cosine of x. And the fourth derivative goes back to sine of x, because derivative of cosine is negative sine and there's already a negative sign in front. That is what we get. So it goes back to this previous one, to the first one. So we get f5 is cosine of x, etc. So that means if I evaluate these at 0, I would get sine of 0, cosine of 0, negative sine of 0, and negative cosine of 0. And then the rest is going to repeat. So what we get is the first term is 0. The second term is 1 over 1 factorial x. The next term is negative 1 over 3 factorial x cubed. So as you see, the even terms, these are all going to become 0. The next one would be 1 over 5 factorial x to the power of 5 minus 1 over 7 factorial x to the power of 7 plus minus etc. Now we would like to write this down using sigma notation. So there are basically 4 pieces to this expression. One is the numerator. So the numerators are all 1. So that would be just 1. Second is the denominator. The denominators are all even factorials. So 1 factorial, 3 factorial, 5 factorial, 7 factorial. So that is 2n plus 1 factorial. I'm sorry, odd factorials. The denominators are all odd factorials. Even numbers are 2n, odd numbers are 2n plus 1. So we can write it down as 2n plus 1 factorial, and then n equals 0 gives us 1 factorial. So we start from 0 all the way to infinity. Now, we also have a power of x. The power of x is the same as the factorial, so this is 2n plus 1. And then we also have a plus minus sign. So plus minus signs are often obtained by powers of negative 1. So negative 1 to even gives you plus 1, negative 1 to odd gives you minus 1. So if you look at the very first term, it is n equals 0 and it's positive. So this term right here, it is positive. So negative 1 to the power of n gives us the correct sign. Negative 1 to the power of 0, it's positive. Negative 1 to the power of 1, it's negative. Negative 1 squared is positive, etc. As you see, the signs are positive, then negative, positive, negative, etc. So this is the formula for sine of x. So sine of x is equal to the sum negative 1 to the n over 2n plus 1 factorial x to the power of n equals 0 to infinity. And this is a very good formula for sine of x. If you want to approximate sine of x, you take the first few terms of this sum, and that would be a very good approximation for sine of x. So the next one is the same thing, but just for cosine of x. So we'll do a very similar, we'll go through this very similar process. So derivative would be minus sine, second derivative would be minus cosine, third derivative would be sine, and fourth derivative goes back to the original function. So this becomes cosine and etc. Now we're going to plug in the values. So we get f of 0 equals 1, f prime of 0, negative 0, negative sine of 0, which is 0, f double prime of 0 is negative 1, f triple prime is 0, and then it repeats. So the Taylor series becomes 1 over 0 factorial x to the power of 0 minus 1 over 2 factorial x squared. As you see, it is plus 1 minus 1. The next one is plus 1 over 4 factorial x to the power of 4 minus 1 over 6 factorial x to the power of 6 plus minus etc. So we can write this as the sum. Again, we have the numerators of 1. The denominators are even factorial, so that's 2n factorial, x to the power of 2n, and n goes from 0 to infinity. The first one is 0 factorial, the next one is 2 factorial, etc. And the coefficients are negative 1 to the power of n. So the signs are negative 1 to the power of n. If it is 0, it's positive. If it is 2 factorial, it is negative. So if n is 1, we get negative 1 to the power of 1, which is a negative sign. So the formula for cosine of x is the sum negative 1 to the power of n over 2n factorial x to the power of 2n. And this is also a very good formula for approximating cosine of x. If you want to approximate cosine of 1, you take the first few terms of this sum and you add them up. And that would give you a very good approximation for cosine of 1. So it turns out that all of these Taylor series that we found are in fact equal to their corresponding functions. Let's look at one more example. Find the two Taylor series of sine of x centered at pi and centered at pi over 2. So this one is a little bit different. So we want to write down sine of x, but we want to write it down as the sum of an x minus pi to the power of n. So this is what we want to do. Okay, so one way of doing this one, and there are a couple different ways of doing this one, but one way would be to use a shortcut, which is using the previous things that we just learned. So we're going to take this one and we're going to call that u. So we're going to write down u as x minus pi, and we are going to evaluate this x from here. So x is going to be u plus pi, and we're going to evaluate sine of x in terms of u. So that would be sine of u plus pi. So if you look at the unit circle, this is u, this would be u plus pi. So this would be u, this is u plus pi. And sine of u is negative sine of pi plus u. So these are negative of each other, which means we can just write down the power series for sine of u. So what was it? We already found that that's negative 1 to the n over 2n plus 1 factorial u to the power of 2n plus 1, n equals 0 to infinity. And all we gotta do is to substitute u by x minus pi, which is what we chose. So this is the sum, n equals 0 to infinity. Now I have a negative sign here. I have negative 1 to the power of n. I can multiply them to get negative 1 to the power of n plus 1 divided by 2n plus 1 factorial. And then we get x minus pi, because u is x minus pi, to the power of 2n plus 1. So this is the Taylor series for sine centered at pi. The next part is Taylor series for sine centered at pi over 2. So we'll do something very similar. So we take u equals x minus pi over 2. So that tells us sine of x is equal to sine of u plus pi over 2, because from here we can see that x is equal to u plus pi over 2. Now, from the unit circle, we can relate sine of x plus pi over 2 with cosine this time. If this is u, this would be u plus pi over 2. Now, sine of this is a positive number, and it's the same as cosine of u. So this one is cosine of u. So those are the same thing. So that's cosine of u. And we have the formula for cosine of u. We already found that. It's the sum from 0 to infinity, negative 1 to the n over 2n factorial, u to the power of 2n. And if we substitute u by x minus pi over 2, we get our Taylor series for sine centered at pi over 2. So this is x minus pi over 2 to the power of 2n. So this is the Taylor series for sine centered at pi over 2. So to summarize, we found that the coefficient of x to the power of n in the Taylor series of a function f centered at 0 is fn of 0, the nth derivative evaluated at 0, divided by n factorial. Similarly, the Taylor series for a function f centered at x0 is sum of fn of x0 divided by n factorial times x minus x0 to the power of n ranges from 0 to infinity. And we found these very important Taylor series. For 1 over 1 minus x, the Taylor series is sum of x to the power of n and goes from 0 to infinity. For e to the power of x, the Taylor series is 1 over n factorial x to the power of n and goes from 0 to infinity. And that is true for all real numbers x. Sine and cosine are going to have the alternating sums. And also we would have 2n plus 1 factorial and 2n factorial at the bottom. And natural log of 1 plus x was sum of negative 1 to the power of n over n plus 1, x to the power of n plus 1, n goes from 0 to infinity. And the range was from negative 1 to 1. Note that if you plug in 1, that also does work. If you plug in 1, you get an alternating sum, which it does converge. And that brings me to the end of this video. I will see you in the next video.